Okay, now that we know that we can make sampling distributions for quantitative data, like means, we can also make confidence intervals and hypothesis tests for means. So the sampling distribution for means, once we checked our conditions, so we had those 3 conditions. We had, it needs to be a random sample like always. It needed to be independent. And so like individuals in a sample need to be independent of each other, and N needs to be less than 10% of the population so that the samples are independent. Okay, and then we also needed, we needed to see that it was nearly normal. And we saw that that was true either if N is greater than 30 by the central limit theorem. It doesn't matter, no matter what, it will be normal. The sampling distribution being it. I'm not very good with my pronouns. Sampling distribution. Okay, or the population distribution is normal. And that will either be stated in the problem, or you graph the sample to see if the shape is approximately normal. So that would be if you're given the data. So that's if you have sample data. Oof, it's hard to write today. Okay. So we had those 3 conditions, and once we checked those 3 conditions were true, we could make our normal curve. And in the normal curve is the average. Okay, and then we went up and down by this formula was our new standard deviation based off of the sample size. Okay, where this guy is the population standard deviation. Okay, so we saw that with sampling distributions. And so now what we're going to see, since we know that our samples can be modeled on a normal curve, we can use samples to understand populations. So this was going from a population to a sample. Now we know that we can go the other way. So we can make, so we're about to do confidence intervals and hypothesis tests. For averages, so quantitative data. Okay, so if we remember a confidence interval from back in the day is a range of possible values. A range of possible values for the population statistic. Based off of, technically it's the population parameter, but it's the population statistic based off of a sample. So before we were looking at percentages and we were like, well, our sample shows that 75% are going to vote, and what would be the percent of the population that will vote? So it ranges from somewhere between like 70 and 80%, something like that. So we're going to do the same thing here. So what we did was we had a guess before. So we have a guess for the population statistic before. We were like, it's p hat. This is our sample percent. That was our guess for the population. But our sample could have been off. So we were like, okay, I think it's p hat. I think it's my sample percent. But based off of a certain confidence, let's say 95% confidence, I could be off by a certain margin of error. So either it could be higher by that margin of error, or lower by that margin of error. And we determine that margin of error based off of, okay, how many standard deviations away from the mean am I? That's z. And then how many standard deviations is that? And so we did p hat q hat over n. So it's z standard deviations. Oops, sorry. Z p hat q hat over n. And we found the z based off of the percent confidence. So here it was like 2 standard deviations away from the mean, so that would, our z is 2. Okay, so this is what we did before, and we're going to do the exact same thing here, except now we're going to look at averages. So let's say, we're going to do an example to come up with the formula here. But it is going to be the same thing. It's going to be our sample average plus or minus a certain number of standard deviations away from that average. Okay, so let's say, so this is when we had percents or categorical data. And now we're going to do quantitative data. So let's say we want to know the average cost of a 4-year college for like per year, the average cost per year of a 4-year college for a Noble student. All right, this is like after financial aid, after grants, scholarships. So like I know I can look up the tuition, right, and find the average tuition, but I want to know after all the like scholarships and stuff, how much do Noble students pay for college on average? So what I'm going to do is I take a sample of 100 Noble seniors randomly. Okay, and these are seniors who are going to 4-year colleges. And I determine the average amount they will spend per year for going to college for tuition. Okay, so the average is, for this group, is, let's say $4,500 per year, so $4,500 per year with a standard deviation of $1,500. Okay, so I want to figure out what's true of the entire population of Noble students. I have what's true for this sample, and I want to know, based off this sample, what is the range of possible averages for the whole population. So I would guess that the population cost is also about $4,500 on average, but I could be off by some margin of error. And our margin of error is based off of a confidence. So let's say I want to be 95% confident. So I'm going to look at this curve. And I'm like, okay, I want this to be my 4,500, but I could be off by a certain margin of error. Now, up here, we knew what our standard deviation formula is, but here we would think that our standard deviation formula, if we remember from our sampling distribution for averages, is the standard deviation of the population over the square root of n. Do we know the population standard deviation? We don't know the population standard deviation. So we don't have the population standard deviation. Okay, so what are we going to do? Oops, sorry. Don't know what happened here. Okay, so we don't have the population standard deviation. what are we going to do? Well, you might say, why don't we just use a standard deviation? We do have the standard deviation of the sample. Okay, yeah, let's do that. So in the center we have 4,500, and instead of using the population standard deviation, let's use the sample standard deviation of $1,500. Okay, but if we do that, that could mean that since we're not using the population standard deviation, we are going to probably have a lot more variation than we normally do. So using the sample standard deviation means that we're going to have more variation. And the book explains this really well. It's chapter 23, and it talks about this guy named Gossett and how he came up with it. So when you have more variation, what you have is really a wider curve. So this would be like the normal curve typically with the population standard deviation. But when we're looking at samples, you have more variation, and so you wind up having a wider curve like this. So fatter tails. Okay, and they talk about Gossett, who came up with it. He was in charge of testing beer for its quality at the Guinness factory. So if you don't know of Guinness, it's a type of beer. And he would send it back if he determined that the batch was bad. So he would take a sample and then test it. And if he was like, based off this sample, I think this whole batch is bad, he would send the whole batch back. But because it was alcohol, he couldn't take super large samples. That would, one, be very unhealthy, and it would probably be really hard to do the math. So he found, what he did was he, based off his small samples, so something with like this wider curve, he found that he sent back a lot of batches that were actually okay. So he said they were bad, but he made a mistake based off his sample. So what he was doing was he was sending so many back that didn't need to be. And that's because he had his variation off. He was using a normal curve, but really it should have been a much wider curve. So what would be 95% in the middle on, or 90, yeah, let's do 95% confidence. What would be 95% on a normal curve? 2.5% here and 2.5% here. If this is 2.5% in this little tiny tail, for you to have 2.5% in the tail on the red curve, you would have to bring it out more because it's a fatter curve, so more fits under there. And so he was getting a z-score of like 2, but really he should be using something that's much wider because the 2.5% in the tails happens much earlier with a fatter tail. So we need to adjust our z-score based off of this sample standard deviation. And so what Gossett wound up calling it, or well, what it wound up being is called a t-distribution. So he came up with something called a t-distribution, and that's what these red curves are, the fatter curves. So he came up with the t-distribution, which is unique to each sample size, a unique curve based on sample size. To account for greater variation. Okay, I'm gonna scoot this up here. So, this is the t-distribution. It accounts for this wider distribution. So our z-score won't be a z-score anymore. What we're going to have now is something called a t-score, or a t-value. So now on t-distributions, we call it a t-value or a t-score. So what we do is we are going to find this t-value for 95% confidence and with a sample size of 100 based off of our problem up here where we took, I believe it was 100 Noble seniors. So our N is 100. Okay, so what we're gonna do is we're gonna be like, okay, that means that I have room for variation, more variation based off my sample. What he came up with is actually something called degrees of freedom in a t-distribution to represent each sample size. So degrees of freedom is how much variation we're allowing. And the degree of freedom is actually the sample size minus 1. The reason why that is it's basically like, think about a soccer team. Okay, you have 11 players, all right, and each player has a position. And so let's say they get to pick their position. You've got 11 players. The first player gets to pick any position. He has freedom to pick and vary between any position he wants. Then the next player has his choice of the remaining 10 positions. And then the next player gets the remaining 9 positions and so on and so on. But the last guy, he doesn't really have a choice as to what position he plays. So he doesn't have any variation in that final position. So really there are only n minus 1 degrees of freedom or degrees of variation because that last position doesn't get any freedom. It's stuck where it is, there's no variation in it. Okay? So it's based off of degrees of freedom. So what we do is we want to go backwards from percent to a t-value, z-score kind of thing. So we're going to use the inverse. We used to use inverse norm. Now we're going to use inverse t. Okay, everything's in the same spot, but instead of using normal stuff, we're going to be using the t distribution now. So I'm going to do the inverse t of what's in the tail, 0.025, and then I need to tell it my degree of freedom. So in this case, it's 100 minus 1. And so what would be 2 on a normal curve, now I need to push it out wider based off of my sample. So I'm going to go to second vars, go to inverse t, 0.025, df of 99. And I get 1.984. Okay, and if you don't have that in your calculator, you can just Google it and just Google inverse t calculator. And the first link should take you to calculating that t-value. There's also a way to do it in the back of the book. So the book, if you go to the very last bit of the book, it's like A120. It's the appendices, so it's like the last pages of the book. A120 has this table, and what it has is DFs over here, and then what is in the tail. So we have 0.025 in the tail, and we have a DF of 99. It doesn't have every DF, so we're going to use 100 because that's the closest that we can get. And we see that it's 1.984. Okay, the best way is really using the calculator or Google to find that t-value, but know that you can in the back of the book. And this is what they show on Khan Academy as well. Okay, so you would find that we have a 95% confidence interval, so there's 0.025 in the tail, and we have a degree of freedom of 100. If we were doing a 90% confidence interval, we would have 0.05 in the tail, and our t-value would be 1.66. If we had a sample size of 20, our DF is 19, and we have a 90% confidence interval, this is our t-value. If we had a 95% confidence interval, this is our t-value. And that's how this chart works. It's A120 in the very, very back of the book. Okay, so we find our t-value, and that's how our standard deviation changes here. So our standard deviation now is using the sample standard deviation So we have the 4,500 in the middle, and then we're going up and down by 150. 150. Okay, so what we're saying is we want to be 4,500 is our guess for our population, but we could be off by a certain amount, and we do that based off of the 95% confidence interval. So 1.984 standard deviations away from the mean, and here is our standard deviation. And so this is our confidence interval, and we type everything in. 297.6. The subtraction side. And the addition side. Okay, so our confidence interval is really, here's the general formula, the sample average plus or minus t specific to your DF, so whatever your DF is what you use, DF being n minus 1, that's what you use to find your t, okay, times the standard deviation. And we use the sample standard deviation, so this is really called your standard error. And this part here is your margin of error. Okay, and we find this t based off of the confidence interval. Okay, and so we interpret it just like we did before. I would say I am 95% confident that the average cost per year of a 4-year college for a Noble student, for all Noble students, is between $4,202 and $4,797 per year. And so this is a confidence interval for an average. Okay? And now you might ask, okay, what about hypotheses tests? Well, they run just the same, except again, we need to consider the fact that we're probably going to be on a t-distribution because we won't know the population standard deviation. So we have to use this t-distribution to allow for that greater variation. So we'll see that right now. So let's say, just move this up here. Okay. Let's say, okay, so let's remember what hypotheses tests look like, right? We have like a statement, and we want to determine something about it. So like, I think the average cost of college for a Noble student is $3,000. Does my sample prove that it's higher? That kind of thing. So you have some predetermined thought, and then you determine if it's right or wrong based off of some hypotheses. So first you write your hypotheses. That's your HO and your HA. And then you might label. That's kind of like sometimes some people do, some people don't. Then you definitely need to check conditions to make sure it's normal, just like we did at the very beginning of this video. You should do that for confidence intervals too. We didn't do that, but we should have. And we want to see if it's unimodal and symmetric. So for sample to see if approximately normal. Then we want to draw our curve. And we put the average in the middle. And we go up and down by, in this case, it's always going to be S over the square root of n because we don't have our population standard deviation. Then we are going to calculate the z-score, only now it's going to be a t-value. Okay, then we're going to calculate our p-value. Instead of using normal CDF, we'll use TCDF. Again, everything's in the same spot and it works the same. It's just that these ones you have to indicate what your sample size is every time because that's what changes the curve. But otherwise, everything's really the same. Okay, and then you interpret. So like reject, HO, or fail to. Okay, so the only difference is now is that when you draw your curve, you're using this new formula for the standard deviation. You're using t-value, which is the same as the z-score really, and you're using t-CDF to find your p-value instead of normal CDF. Your hypotheses also are not going to be p's anymore because you're not talking about percentages. You're talking about averages, so it's going to be the mean, this guy. Okay, and this will be equal some number. This will be less than, greater than, or not equal to some number. Okay, but the steps are truly the same. So let's see it now. I think my proposal is that, there's not a lot of room here. I think manicures are $20 on average in Chicago. I don't know. I don't get my nails done. You guys know this. You can see my nails every day. Okay, but my sister, who does get her nails done, she thinks that it's higher. So what she does is she goes out and picks a stratified sample of nail salons, one from each neighborhood. And gets a sample of 60. She has an outlier though, so she needs to remove that. She has an outlier. She checked with the box plot and eliminates that outlier. So her sample is 59. The average of that sample is $28 with an SD of $8. Okay, does she have evidence to show that it should be higher? So what I'm going to do is start with my hypotheses. I think it's $20. So the proposed average is $20. So mu, our average, is $20, but she thinks what she wants to show is that it's higher than $20. Okay, and so she has a sample of 59. The average of that sample, we call that X bar, is 28. And the standard deviation of that sample is 8. Okay, and so we need to check conditions on our sample. And so those 3 conditions that we check, I'm just going to scooch this up. Are, it needs to be random. And that's stated, that she took a random stratified sample. It needs to be independent and small enough for independence. So one nail salon does not affect another. But really, we want to make sure that 59 is less than 10% of all nail salons in Chicago, and that's definitely true. There's probably more than 500 nail salons in Chicago. And then we need to make sure it's normal. So distribution, the sampling distribution will be normal. We don't know if the sample is normal. We don't know if the population is normal, but it doesn't matter because n is 59. So by the central limit theorem, since n is greater than 30. Okay, so we know it will be a normal distribution, so we could draw it. And we're assuming that the average is 20. We don't know the standard deviation of the population, so we use this S to find that standard deviation, and knowing that there's going to be more variation, so it's really a t distribution. This is 1.04. Okay, so what we have here, we want to know how far away our average is. So we did conditions, we drew our curve, now we need to calculate the t-value, which is just like the z-score. How many standard deviations away from the average is our sample? Okay, so our sample is 28 minus the center, which is 20, should be 25, but divided by the standard deviation, which is 1.04. So this is going to be a big value, 7.69. And then to find our p-value, we use t-CDF, because now what we need to make sure we see here is that we have fatter tails because we are using this sample standard deviation. So we go to second vars, and we see, oh, I didn't click second vars, and we see normal CDF like we normally use, inverse norm like we normally use, but now we're using inverse T and T-CDF. So we'll use T-CDF, and our T value is 7.69, and it says greater than, so we're going to go to positive 999, and now we need to include our DF, which is 59 minus 1. So our DF is the sample minus 1, so 58. Oops. And we get 1.01 times 10 to the negative 10th is our p-value. And this was T-CDF 7.69 to 999, and with a DF of 58. Okay, and so that's our p-value, which is tiny, tiny, tiny. So just like before, if your p-value is low, you reject the HO. So we're going to reject the HO. Our p-value is low. Since p-value is low, is below 5%, we reject HO. It was impossible to get that sample if the average was 20. It was just impossible to get this average. But she did get that average. So this must not have been true. It must be that the average is greater than 20. So since the p-value is below 5%, we reject HO, and we have evidence to show the average manicure cost in Chicago is over $20. Okay, and so this is a hypothesis test with averages. and a confidence interval with averages. Okay, I'm gonna give you guys one to try and then go through those. All right, let's start new guy here. So you try. All right, you wanna know the average number of pets. Not including fish. Fish don't count. No offense. Per household in Chicago. You gather a random sample of 50 and find the average to be 1.8 with a standard deviation of 0.6. An article proposes the average pets per household, pets per household is 1.5. Do you have evidence to show it's higher? Go ahead and try that out. Pause the video, try it out yourself. I'm gonna go through it. Just start the video again once you've tried it. Okay, so our HO is that the average is 1.5. That's what the article says. But based off our sample, we want to show that it's higher than 1.5. So our sample was 50 houses. The average was 1.8 and the standard deviation was 0.6. Our DF then, just for our future, is going to be 50 minus 1, 49. Okay, so we've labeled and we've done our hypotheses. Now we check conditions. Stated random. Independent. 50 is less than 10% of all Chicago households. Yeah, there's like millions. And normal, approximately normal distribution based off of CLT, central limit theorem. So because 50 is greater than or equal to 30. Okay, so central limit theorem will apply. So we make our curve. In the middle of the curve is 1.5, and we go up and down by, divided by the square root of 50. Ah, 0.6 divided by the square root of 50, 0.084. Okay, so we go up and down by 0.084, so this is 1.584, 1.668, and then, well, it's really 0.085, shoot dang. Hang on. 5. So this is 70, and then 1.755. Okay. So now we're like, okay, so where does our sample lie? So T is 1.8 minus the center divided by that standard deviation. And we get 3.53. And now we need to find our p-values. So we're out here and we want to go higher. So 3.53 to 999, and we're using TCDF instead of normal CDF. And then, so that means it's going to ask us what's our sample, what's our degree of freedom. So our degree of freedom is 49. And that way it can adjust to the sample size. So it makes the tails a little bit fatter. And so you get 0.00046. So still a really small p-value, so we reject HO and have evidence to show the average number of pets per household in Chicago is higher than 1.5. Okay, and so now let's do a U-try with confidence interval. So construct a 90% confidence interval for the number of pets, for the average number of pets per household in Chicago. Okay, so remember the formula is our sample, but our sample could be off by a margin of error. Okay, this t is not the same t as here. This is a t based off of your confidence. So if we have a 90% confidence, that means there's 5% in each tail. How many standard deviations away from the mean is that t? So it's not this t. We actually need to find this t by saying the inverse t of our tail area is 0.05 and our df is 49. We need to find that t value. Inverse t, 0.05, 49. And we get 1.677. It's 6765. Okay, so that's the t value we use here, because what we're saying is we want to know this range of values that's within 90%. It has nothing to do with the hypothesis test. So we take our sample average, which was 1.8, plus or minus this 1.676 standard deviations away from the center, and then our standard deviation was 0.6 over the square root of 50, which is 0.085. And so this is 1.8 plus or minus 1.43, 1.425. Oops, 0.1425. So this is 1.9425 and 1.65. So 90% confident that the average pets per household in all of Chicago is 1.65, 1.66 to 1.94. Okay. All right, that's it. Good luck on Khan Academy. You'll be reviewing all of this stuff.